Hello dear students, in this numerical a system of springs are given and their arrangement is shown here. We have to determine here the overall stiffness matrix. So we have to determine here we have to find out here the global stiffness matrix, and we have to find out the deflection of each spring. Now if you look at here in this figure, how many springs are given? Spring number 1, 2, 3, 4 and 5. Total 5 springs are given here. So we have to find out the deflection in each spring. So for this we are going to solve to find out these two values. So first step in solving this numerical, as discussed when in last lecture also, first step is discretization. So this is a problem of 1D. So if you observe here, this is a fixed support which is given, 5 springs are given, their arrangement is given, and at the other end a force of 25 Newton is acting here. So considering this, this is a 1D problem, it was fixed. So all these node point will consider as 1. As it was a fixed support, here we will get a reaction. So here is a reaction. Now this is node number 1, 2, this will be node number 2. Now as these three element number 1, element number 2, element number 3 are connected to the same platform, all these will be element number 2, node number 2, node number 2. This will be node number 2 to 3 and it will be from 1 to 3. Values of stiffness are given in the numerical. K1 is given as 20 Newton per mm. K2 is given as 10 Newton per mm. K3 is given as 20 Newton per mm. K4 is given as 50 Newton per mm, and K5 is given as 25 Newton per mm. So these are the values of stiffness for this individual spring. This is for K1, this is K2, this is for K3, here is K4, and it will be for K5 will be here. Now after the discretization, the important step is to plot the element connectivity in a table form. So let's plot this table of element connectivity. This is a very important step because all the matrix that we are going to combine, they are based on this table. So here element number. Now if you look at here, how many elements are given in this numerical? 1, 2, 3, 4, total 5 elements are there, and global node number of, we have to find out here global node number of local node 1 and local node 2. So when we are considering this global node number of, now the element number 1, it is connected between 1 to 2. So its global node number are 1 to 2. Similarly, for element number 2, element number 3, they are connected between 1 to 2 only. So here we are considering 1 to 2. Here also we are considering 1 to 2. After this, the element number 4. The element number 4, if we are considering it into local coordinate system, this will be 1, this will be 2. Now this 1 in global coordinate, it is 2, and this 2 in local 2 in global coordinate system, it is 3. So it is connected between 2 to 3, and this element number 5 is connected between 1 to 3. So here it is, we can write down here that this element number 4, it connected between 2 to 3 and it is connected between 1 to 3. So these are nothing but these are our element connectivity. So based on this, we have to find out the dimension of global stiffness matrix K. It is found out by n by 1, n by n. the dimension of global load vector F and the dimension of global displacement vector, it is found out as n by 1 and n by 1, where n is the total degree of freedom, the total DOF. Now, how to find out the total DOF? Degree of freedom per node. So, as this is a 1D problem, degree of freedom per node will be 1 into number of nodes. So, if you observe here, the number of nodes are 1, 2, 3 only. So, it is total degree of freedom per node, it is 1 into number of nodes 3. So, it is nothing but 3. So, total degree of freedom for this assembly is 3. So, these dimensions we will get as, it will be 3 into 3, it will be 3 into 1 and it will be also 3 into 1. Now, we are going to see the individual elements. For individual element, we are going to see the individual stiffness matrix. So, here we will start with K1. The formula for K, I will write down first the formula for K. K stands for the stiffness, K minus K minus K, K. So, for first element, we will write here so that it will save our time while combination of the global stiffness matrix. How we will get the global stiffness matrix? K is equal to K1 plus K2 plus K3 plus K4 plus K5, as there are 5 different elements are there in this numerical. So, let's write down K1. Value of K1 for element number 1, it is given in the numerical. See here, value of K1 20, K2, K3, K4, K5. Please note down these values. So, K1 is 20. So, I am writing here 20 minus 20 minus 20, 20. Now, we have to write down here the global degree of freedom for this K1 matrix. So, how to find out this global degree of freedom? From this element connectivity table. For element number 1, it is connected between 1 to 2. So, simply write here 1, 2, 1, 2. These are the degree of freedom. Now, we will move forward to K2. So, here will be plus sign as we are going to do the addition. Here for K2, the value is 10. Look at here. I will show you. The value is 10 Newton per mm. So, considering this value 10 minus 10 minus 10, 10. Our formula is K minus K minus K, K. So, based on this formula, we are just putting the values here for the element number 2. Now, for element number 2, it is also connected between element 2 and 3 are connected between 1 to 2 only. So, considering this 1, 2, 1, 2. Now, the element number 3. Now, the third element, the stiffness is 20. So, 20 minus 20 minus 20, 20 plus element number 4. And this element number 3 is also connected between 1 to 2. 1 to 2. Now, the next K4. K4 is connected between, this is element number 4, sorry, element number 4, it is connected between 2 to 3. So, its dimension, now it will be 2, 3, 2, 3. And the stiffness for this is 50. It is given in the numerical 50 minus 50 minus 50, 50 plus the last stiffness matrix that we have to write is K5, and for K5, look at here, the value is given as 20 Newton per mm and it is connected between, we have to look at this element connectivity 1 to 3. So, it will be K5 will be, its stiffness given is 25. So, it is 25 minus 25 minus 25, 25, and it is connected between 1 to 3. So, I am writing here the degree of freedom 1 to 3 and 1, 3. Now addition of this K1, K2, K3, K4, K5, addition of this will be give us the global stiffness matrix. So I am here creating the global stiffness matrix, and the dimension for this global stiffness matrix will be, look at here, 3 by 3. So its dimension will be 3 by 3. So it is 1, 2, let me change the color. So it will be 1, 2, 3, 1, 2, 3. These horizontals are rows. This is first row, second row, third row. Similarly, this is first column, second column, and third column. So if I want to find out the dimension of this, how we can say this dimension? It is in second row, second column. Dimension of this, it is in third row, third column. Dimension of this, it is in first row, first column. Similarly, we have to place the all elements from this 5 matrix. So if you are going to look at here, 20 minus 20 minus 20 20, it is between 1 to 1 2. So it will be written as 20 minus 20 minus 20 20. Now after this, let me increase this space because here is a major calculation part is there. So what we will do quickly, I will increase this space, as we are going to combine the 5 matrix together. So what we need here, the space. So okay, now it will be fine. 1 2 3 1 2 3. So first matrix I am placing here 20 minus 20 minus 20 20. It is between 1 to 2. So simply you can write down like this: 20 here minus 20 here, second row first column minus 20, and write down here 20. Now looking at the second element, this is our K2. It is also placed between 1 to 1 2. So it will be 10 minus 10 minus 10 10. It will be go in the form of addition. So here 10 minus 10 minus 10 plus 10, the element number 3, and for this is a K3. 20 minus 20 minus 20 20. Location is also 1 to 1 2. If you are having any doubt in this particular step, feel free to contact me on WhatsApp. So it will be plus 20. Sorry, it will be second element is minus 20, whose location is first row second column. How? Look at here, it is in this minus 20 first row second column. So we are putting it here, minus 20 plus 20. Now the next K4. Now for K4, see the location, it is in second, here second row third column, second row third row second column third column. So the dimension of this particular 50, if you look at here, the dimension of this 50 will be, it is in second row second column. So look at here, this second row second column. So here it is second row second column. So it will go like plus 50. After this particular element, and location of this, it is in second row. See here, it is in second row third column. So look at here, second row third column. So this element will be here. So considering it as minus 50. This is, then location for this, it is in third row second column. So third row second column, here it is minus 50, and the last location is third row third column. So here is 50. So here is 50. So after this, the last element that is pending is K5. So for this K5, it is in first row first column. So here will be plus 25. This particular element, first row third column. So first row third column, here it is. So it will be minus 25. It is in third row first column. So here it is third row first column. This is the location. It will be minus 25. And the last one, third row, third column. So it will be plus 25. In this way we have to combine, and this particular step is very important because if you done some mistake here, your whole numerical will get wrong. So quickly we will do the addition of this. So let's write here only the addition of this: 20 plus 10, 30 plus 20, 50, 60, 70, 75. So this particular point, at this particular point we will get is equal to 75. Let me change the color so it will be very clearly visible. So addition of this will be 75. Similarly this addition is minus 50, 20, 10, 20, minus 50. This will be minus 25. This will be minus 50. Now here 20 plus 10, 30 plus 20, 50 plus 50, 100. Here it is minus 50, it is minus 25, minus 50, and this will be 75. Now using our formula of force is equal to global stiffness matrix into the nodal displacement. So this force, now force matrix will be 3 by 1, as we have already found out this dimension. This will be 3 by 3, this is 3 by 1. Now the force F1, F2, F3 is equal to this stiffness matrix we have just derived. So I will write here only the final figure: 75 minus 50 minus 25 minus 25 minus 50 100 minus 50 minus 25 minus 50 and 75. The dimension of this is 1, 2, 3, 1, 2, 3 into the nodal displacement. And nodal displacement for node number 1 it is u2, for node number 2 u2, for node number 3 u3. Now we want to find out this value f1, f2, f3. We will put these values here. So if you look at here in the figure of discretization, the f1 value, the force at f1 is nothing but r. There is no force at node number 2 is given, no force here, so it will be 0. And at node number 3 force of 25 Newton is acting. So we will put these values here in this numerical, in this equation actually. So here it will be, this value will be r. No force at node number 2, and at node number 3 force is 25. So now using the elimination approach, what we do in the elimination approach, using elimination approach, which node number is fixed here? Here if you observe, the node number 1 is fixed. Here the fixed support is given. So as this node number 1 is fixed, using the elimination approach, what we have to do here, we will simply cancel this first row, this is our first row, and first column we will simply cancel. So what is remaining now? We are only having this 2 by 2. So we will solve this. This is our elimination approach. If the node number 3 is fixed in any numerical, node number 3 is fixed, then what we will do? We will cancel third row, third column. Here node number 1 is fixed. That's why we have cancelled first row as well as first column. So what is remaining now? We will solve 0 is equal to 100 into u2 minus 50 into u3. Similarly here 25 is equal to minus 50 into u2 plus 75 into u3. So after solving this, please try to pause this video, try to solve this, and please check whether you are getting the same values what I am writing here. So after solving, we will get u2 is equal to 0.25 mm and U3 is equal to 0.5 mm. So these are the value of U2 and U3 that we are getting here. U2 is equal to 0.25 mm and U3 is equal to 0.5 mm. Now the first thing that we need to find out is the deflection that we have find out. Global stiffness matrix also we have find out. Now we will find out the deflection in each spring. Now as the spring number 1, spring number 2 and spring number 3 are connected like this, that their node points are similar. They are connected between node 1, 2, 3. So how to find out its deflection? It will be simply U2 displacement at node number 2 minus the displacement at node number 1. So for deflection of spring 1, 2 and 3, it will be find out as U2 minus U1. So 0.25 is the value of U2 minus, as U1, the node number 1 is fixed, so U1 will be 0. So deflection of first spring that we are getting here, 0.25 minus 0, so we will get as 0.25 mm. Now the deflection of here spring number 4, here it is. Oh, sorry. How we will find out? U3 minus U2, as it is connected between node number 3 and node number 2. So deflection of spring 4 will be U3 minus U2. So 0.5 minus 0.25 will give us 0.25 mm. And the deflection of spring 5, as it is spring 5, look at here, it is connected between spring 5 is connected between 1 to 3. So it will be U3 minus U1. So U3 minus U1. So it is 0.5 minus this 0 is equal to 0.5 mm. So in this way we have solved this numerical. Please make sure to comment your name in the comment section so that I will consider it as your attendance. Thank you so much.